Hello all, welcome back to our channel, and today's video is about using an operational amplifier as a comparator. So as you might want to recall, if you are already subscribed to the channel, we have a couple of videos on comparator circuit and where we explain to you what is a comparator, how it works, and there is another video about whether or not an op-amp operational amplifier or any high gain amplifier for that matter can be used as an amplifier or not. And we had talked about the pros and cons. So this time I am going to demonstrate you through some circuit simulations about the working principle of the comparator, how it is going to operate. So let's say you have this task of designing a comparator. So right now on your screen, as you can see, I have taken from the device library of this circuit simulator a simple operational amplifier. If I right click, it shows me this is a precision operational amplifier. Okay, so it has power supply rails, that is negative and the positive. Name of this component is designated as U1. The IC or the part number of operational amplifier is OP77. So if you actually want to see the details about this operational amplifier, you can just type this number on Google and search for its data sheet. However, that's not our full purpose here. Rather, our purpose is to understand how this operational amplifier will act as a comparator. So it has two inputs, positive input and the negative input. And to the positive input, I will have the external input supply or external input that will come. And to the negative input, I apply a reference voltage. Let's say I apply a reference voltage as 0 volt or simply a ground. So the comparator works like this. It has two inputs. To the positive input, I have an input signal V in. If that V in signal, which is an input signal, is greater than the input at the negative terminal of op-amp, then the output will saturate or switch to the positive supply rail of the operational amplifier. I repeat, if the input at the positive terminal of op-amp is greater than the input at the negative terminal, the output will switch to the positive supply rail of the op-amp. On the other hand, if the input at the positive of the op-amp is less than the input at the negative terminal of op-amp, the output will switch to the negative rail of the op-amp. So what is the positive rail of the op-amp? It's the supply voltage V plus, which is given by this external voltage source. So you see this voltage source has a voltage of V volt. In this case, I have used, let's say 12 volt, and that is the net that is labeled as V plus is coming right here. On the other hand, the negative supply rail of the operational amplifier is connected to the 0. So when the op-amp output will switch between V plus and 0, V plus and the ground, or 12 volt and the ground. So to demonstrate that, I will run the DC operating point analysis, which is indicated by the .op command. So I have already explained in so many other videos about how to pick up the components from the library, such as operational amplifier, such as voltage source, such as ground, and some other passives. And I have also explained to you in detail how to make the connections through the wires, how to label the nets, and also on. So for example, if I right click this net and I will select highlight net, you see that this V plus, that is a positive power supply rail of the op-amp, is connected right here. Okay, so you might want to refer to that. Once you make the components, from the library, you pick up them, you place them on the schematic editor, you make them connect together, you label the net, you make the wire connection, everything is done. Next step is to provide the numbers. For example, I right click this supply and I have used the DC voltage of 1 volt at the positive input of the op amp. So this voltage of 1 volt is connected here. So apparently this 1 volt at the positive is greater than the input connected to the negative of the op amp, and essentially the ground is connected to the negative input of the op amp. So as I explained, the output should switch to the positive supply rail of the op amp. If I will use negative one, for example, let's say I type negative one. So now the input at the positive terminal of the op amp is less than the input at the negative terminal of the op amp. So as I explained to you earlier, the output of the op amp, which is V out, should switch to zero, the ground. Okay. So let us verify that. So to verify that, what I have done, I have clicked the simulate button. Then I click the edit simulation command. Then it opens me this window. And from so many analysis, I have selected the DC operating point. So this analysis helps me to compute the DC operating point, treating all the capacitances as open circuit and inductances as short circuit. And the syntax for that is .op. So when I click OK, this analysis command comes on the screen. So we don't have any external capacitances and inductances, but if they are, they will be treated as open circuit and short circuit respectively. Now let's start running this analysis. So I'll start with plus 1 volt and I will run the command. Output should reach to V plus, which is the positive supply rail, and it is 12 volt. So you can right click here. I have used 12 volt power supply. So let's run. So I see here this operating point window prints all the voltages and the currents. So voltage at node 001 is 1 volt. So this voltage is what is this voltage? We'll see that. This is this one. This is the node 001 actually. This is that net. Okay, I can label it the net also. And then if I label this net, then the voltage at that labeled net will be printed here. So output, the input voltage is 1 volt. Then the next is V of V plus. That is our positive rail supply here, which is 12 volt is showing me. Then next output voltage is, as expected, has switched to the positive rail because the positive input is greater than the negative input of the op amp. So output is 11.35. So we expected 12 volt, but it is 11.35. So it's about 0.65 loss. So that loss can be attributed to some internal analysis of internal things in the circuit. Now the circuit, the current drawn by the V input is this current that is shown right over here. This number is a little bit questionable, that is minus 61.78 amperes, so it's quite huge. Then this is the current drawn from the supply cell, which is like 0.8 milliampere, reasonable. And this is how it is shown over. So you can see now I got positive input greater than the negative input, output is positive. Now I do one thing, I take the minus 1 volt and output should switch to negative supply of the op amp, which is 0 volt. So let's see, let's run. So as you can see that the voltage at the node 001, which is my input, is -1, and this is the power supply rail 12 volt, but output, which is our concern, has switched to 0.64 volt. So initially it was 11.6 that is the positive supply, but now it's switched directly to 0 volt, close to 0 volt, that is 0.64 volt. So you see how simple amplifier is acting as a switching circuit, or as a, let's say, a comparator. It compares the two input, accordingly switches the output. What if I use, instead of 0, I use a ground, I use some reference voltage. So for the reference voltage, what I need to do, I need to connect a DC voltage source here, and then my input voltage will be compared to that DC voltage. So let's see how we can do that, and accordingly we can plot that. So let me do one thing. I will pick up the library and then I will type volt. There is a voltage source. Then I'll click OK. Then I will, let's say, connect it here. I'll press the space button on the keyboard. Then I'll cut this right here. Then I'll move this. For example, I move it. Oh, not like this. Is V2. Rather, I need to move this voltage source of the ground. Then I'll put it here, and let me make the wire connection. So I am just using the wires right here, uh, and that's it. And then I will just do like this, keep this somewhere here. Now how much voltage I want to use? For example, I use right click here and I use the value of 1. So now if I use -1 and compare it with 1, the output should be negative, switching to the negative supply. And if I use the positive one, then both inputs are same. So we'll see that. But if I use the positive 2 volt, then output should switch to V plus, that is positive supply range. So let's start with this. So to the positive input of the op amp, I have -1, and to the negative input of the op amp, I have +1. So let's see how the output behaves. Click run. So as you can see, output is output right here is again 0 point, close to 0.64, which is close to 0 volt. So as expected. How about I change it to, let's say, 2 volt. So obviously output should switch to V plus, which is positive supply of the 1. So it should be close to 12 volts. So let's run the analysis again. That's correct. So you have 11.35 and so on, right? So we can run the DC analysis also. Let's say, for example, you keep this voltage as a reference voltage, which is constant at 1 volt, and then you sweep this voltage source, and accordingly you see how the output varies. Okay, so for that we need to run the DC analysis. So click simulate, click edit simulation command, click DC sweep, and name of the first source to sweep. So what is the name of the source you want to sweep? This is V in. Then type of sweep, let's say linear. Start value, let's say 0. Let's say 3 volt, or let's say 5 volt. And increment is about 1 volt. So we'll click here and then we'll put this command right here. As soon as you put this DC analysis, with this, you see there was dot here, but now there is this comma. So you can see that this command, when the such thing happens, you say this command is disabled because this command is got enabled. Okay, so now you are sweeping the DC voltage source at the input, positive input of op amp from 0 to 5 volt at the step of 1 volt. So it will start from 0, then 1, then 2, up to 5. And it will always compare the with the another voltage source, which is reference voltage source at the negative. Accordingly, output will be making the switch. Let's run this analysis. That's it. So these two graphs I don't want. These are some other circuitries. So let's tile the windows. That's it. Now what I want to do, I first want to plot V input and see how it is. So you see there is a linear variation from 0 to 5 volt. And now on the same window, I see, let's say V2, which is reference volt, which is all the way constant, with the blue. So now you see plot the output. Now you can see when your input green is less than your reference blue, which is up to 1 volt, your output is switching to, can you see that? Let me just explain you again. So when your input is below the reference voltage, which is the green line is below the blue line, your output is uh, like red, which is giving up to 0 volt. It is actually increasing linearly as your input increases, but is as long as the input stays below the reference voltage, your output is linearly increasing. But after that, your input crosses the reference voltage, output switches to the positive supply rail. Okay, so this is something you have to understand, like your input is below the reference voltage, so why your output is not 0 volt till that time. So let us figure that out. So after that, I am going to now show you the transient response of this circuit. So for example, I will use the time, I will apply the time varying waveform or voltage at the positive input, and then I will apply the reference voltage at the negative input, which is already I have done. And but this will be a DC voltage and this will be a time varying voltage, and accordingly I will show you how the output will be switching. So let's say you have a reference voltage set to 0, which is a DC value, and then let's say you want to apply a time varying voltage here. So right click here. Now you have used the DC value in the earlier analysis. Click advanced and choose pulse, so which is basically having two values. So initial values, let's say it has 0, it starts, then V on is the value you can get, or for example yeah, V on, so let's say it goes to 5 volt and number of cycles would be 10. So this waveform is switching between 0 to 5 volts. Okay, and there is a delay of, let's say, 0, rise time is 0, fall time is 0, and how much time it is on, that you need to understand. So for example, I keep it on for 1 second, or let's say 100 milliseconds. So it will switch between 0 to 5 volt, and that switch on time of that pulse will be 100 millisecond, and then there'll be a period. So let's say period we have to understand. So we'll write the period now. Let me just figure that out. So let's call it like 200 milliseconds. That is time period, total time period. Okay, so we'll see how much it goes, and number of cycle 10. So click OK, and there is a pulse that you have applied. So just move it maybe somewhere here. Yeah, keep it here. That's it. Now you have to run the time domain analysis. So DC and operating point won't work. So edit simulation command and transient, select transient, stop time. Stop time you have to understand. So let's say you want to, your total time period is 200 milliseconds. So let's say 500 millisecond. Time to start saving data from 0, maximum time state. You can keep it empty also, because then it will choose itself. Now you see, as soon as you select the transient analysis, .dc analysis got disabled. So let's run this. So now your input is switching between 0 and 5 volt. So it's the pulse drain that is coming to the positive input, and your other input of the op-amp is fixed at 0. So we'll see how the op-amp output is switching. So click OK. Let's first click the input. This is your input waveform. As you can see, the time period is about 100 milliseconds. It's not very perfect square wave or pulse, but still it is. Now reference is set to 0 and then plot the output. So you actually can see that the output is also being shown right here. So what I'll do, your input is switching between 0 to 5 volt and the output will see how much is the switching. So zoom to fit and then add plot pane, and output input can be right here, and then your reference can also be here, and the output is actually you can see how's output there. So when your input is 5 volt, which is greater than the reference 0 volt, your output is switching to the positive side, which is your supply voltage, positive supply, correct? When the input is 0, which is reference is also 0, and then your input falls below the reference, so therefore the output is actually 0. Not output is not actually 0 because your input is not falling to 0. Output is slightly degraded from 11.38 to 11.12, right? So you basically have to say start from minus 0.5 to plus 5. So now this will be better. That's correct. Now you see your input is green, which is greater than the, let me use the laser here. That's much better to explain things. So right here, so green is greater than the blue, output is switching to positive rail. When the green falls below the blue, which is 0, and the input falls to minus 5, the output falls to how much? Let me see. Yeah, output falls to 0, right? You see output is switching to 0. Again, when your input rises and it is greater than the blue curve, which is at the negative input, the output is positive. So that's it. So you basically see it is like uh, your waveform. It is converting the input waveform to a perfect square wave. Okay, so it's also called a square wave generator. What about you have like a sinusoidal waveform? Can we do that? So just click here, select sine, DC offset. Let's keep it like you want to keep it 0. Why not? And amplitude is 5 volt, and frequency is, let's say, 1 kilohertz. Time delay and theta, everything is 0. Phi, you don't care, and number of cycle, let's say 10. Let's see how the circuit will behave to the sine wave. Okay, voila. So if you see that, very good output you see right here. So you have input as a sinusoidal. When input is greater than the blue curve, the green is up. The blue curve, your output is 12 volt. Very good. When input falls below the blue, output is 0. And so it is also, the circuit is also working as a perfect sine to square wave converter. So you also can call it analog to digital converter. Now this little bit rise and fall time that you can see, it is not a perfect square wave. That is coming from this internal operational amplifier parameters. That is because of the operational amplifier. So you are interested in this segment of the waveform. So that's good. So we've seen that how the circuit works as a comparator and how you can run the analysis for this circuit. So that's all. Just an exercise. I will encourage you to change some reference voltage. Let's say you add it like -1, and accordingly your output will be different. Let's see now how the output works. You see the reference is now -1 constant, and accordingly the output is responding. And this is how you can play with this circuit. So hope you like this video about using simulating the circuit of a comparator, turning high gain amplifier as a comparator. You ran the DC operating point analysis with the DC voltages. You see the how the comparator switches the states, whether positive or negative. Then you also saw the DC sweep analysis where your input is varying, and then you see the transient response of this circuit. So if you like this video, click the like button, share it with others for wider reach, and do comment, subscribe to the channel, and stay tuned for more technically rich content. Till then, wish you happy learning.